Hello! This is me, checking to see if I'm live. Am I live? I'm gonna assume that it's gonna go live in a minute. Okay. It's time to start talking about alternating series. So far, everything we've done has been positive series. By which I mean about series of positive terms. I don't think we've ever talked about one with a series of negative terms, but that works just the same. You can factor out a negative one and it turns into a series of positive terms. And factoring a negative out of the series does the same thing as factoring out of the partial sums, and you can factor it out of the limit. So the limit of the partial sums of the opposites is the opposite of the limit of the partial sums. The negative comes out, everything's fair game. Yeah, everything's fine if you pull out a negative. If all the terms of your series are positive, or if all the terms of your series are negative, there's some types of statements that you would like to make that turn out they are true. Here, let me tell you an example. Consider, we said that the sum from n equals 1 to infinity of 1 over 2 to the n, that was our first geometric series, and we evaluated it, and it was 1. So this is 1 over 2 to the 1, plus 1 over 2 to the 2, plus 1 over 2 to the 3, plus 1 over 2 to the 4, plus ... does equal 1. Well, when you add up numbers, you're allowed to rearrange them, right? We use that a lot in math, all the time. It's important and it's fundamental. I want to try rearranging these. First, I want to take out all the odd terms. And now I want to take all the even terms. Uh, 2 to the 8. Do I still get 1? This is not obvious. Let's check it out. Here, this is 1/2, 1/8, 1/16, 1 over 32. If I think about consecutive terms, we're multiplying by 1/4 every step, right? So this is also geometric. Its sum is first term over 1 minus r, or I guess I should note that r is 1/4, does have absolute value less than 1, so it does converge. And the thing it converges to is first term over 1 minus r is 1/2 over 1 minus 1/4. That's 1/2 over 3/4. That's 1/2 times 4/3 is 2/3. What about this? What does it converge to? This is 1/4 plus... I messed this up. I just included that. That one shouldn't have been there. Because 4 is not even. So 1, 3, 5 are the odds. And yes, we were multiplying by 1/4. If I had skipped that like I was supposed to. Okay, this one is 1/4 plus 1/16 plus 1 over, what's 2 to the 6? That's 2 cubed squared. That's 8 squared is 64. The next one, we're multiplying by 1/4 every step. Again, we have a geometric series that also converges. This first series was 2/3. The series of the even terms turns out to be, again, it's geometric. Again, we can add it up, and it's first term over 1 minus r. That's 1/4 over 1 minus 1/4. That's 1/4 over 3/4 is 1/4 times 4/3 is 1/3. The first series adds up to 2/3. The second series adds up to 1/3. And this adds up to 1. And cool. We get the same thing just like we expected. Rearranging the order didn't make a difference. Rearranging the order is suspect when I've got this infinite thing. Like, once I have infinitely many terms, nobody ever promised us that when we rearrange the order we will still get the same series. But in this case it turned out we did. And we can do this in even grosser ways. if I consider, let's add up all the odd terms. Let's add up all the double the odd terms. So double every odd number. Double 3 is 6, double 5 is 10, double 4 is, double 7 is 14. Now let's do quadruple all the odd terms. 2 to the quadruple 1 is 1, quadruple 3 is 12, quadruple 5 is 20, quadruple 7 is 28. Now let's do 2, 4, let's do 8 times all the odd terms. 1 over 2 to the 8, plus 1 over 2 to the 3 times 8 is 24, 2 to the 8 times 5 is 40, 8 times 7 is 56. The next one would be 16 times every odd term, 2 to the 16, 3 times 16 is 48, and so on. These are the odd terms. These are double and odd number terms. These are quadruple and odd. And so on and so on. And I guess I'm not going to go through and do each of these, but it's sort of a worthwhile exercise to do. We can do geometric series. Each of these series turns out to be a geometric series, and I believe that the resulting sums, when you add them up, they are also geometric. I guess, hey, I didn't talk about the fact, but note, every number is in here exactly once. Every positive integer can be written uniquely. As a power of 2 times an odd. Every number is either odd or it's divisible by 2. Keep dividing by 2 and eventually you'll get an odd. So every positive integer can be written uniquely as 2 to the n times 2k plus 1 for some n greater than or equal to 0, k greater than or equal to also 0. So you're always an odd number times a power of 2. Keep dividing off the 2's and eventually it'll be odd. There's the odd. Count how many times you have to divide by 2. There's the power of 2. So every number is in this series somewhere. We have added up all the terms, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 5, 6, 7, 8, 9 will be with the odds, 10, 11's with the odds, 12, like everything's in here, and it's in here once. We've added up everything once, and we do end up with 1. And we could state the theorem about rearrangements. It's very difficult to state correctly because there's like weird ways of rearranging like this, but it turns out that if you rearrange a series of positive terms, you will get the same sum. Notice there's an asterisk in here. This works on series of positive terms, which is everything we've talked about so far. Or it also works for all negative. It's difficult to work with series that aren't all positive or all negative. And let's take an example of this. And the key thing we're headed to is this thing I just said was true for positive series is not true when you have things that are mixed. Let's consider the alternating harmonic series. The alternating harmonic series is the sum from n equals 1 to infinity. 1 over n is the harmonic series. We're going to add a negative 1 to the n to make it alternate. Remember, negative 1 to the n is negative 1, positive 1, negative 1, positive 1. So when we talk about this, when I talk about n equals 1, I get negative 1 over 1, positive 1 over 2. Negative 1 over 3, positive 1 over 4. Negative 1 over 5, positive 1 over 6. ... Does this converge? Well, let's think about it. Our first term is negative 1. Let's think about our sequence of partial sums. S0 is the sum of no terms, is defined to be 0. S1 is the first term, is negative 1. S2 is negative 1 plus a half, so from here I need to move to the right by 1/2. So this is negative 1/2 at S1. Now I need to move backwards by 1/3 to get to S2. Now I need to move... oh wait, I've got them wrong. This one was S2 and that one was S3. Now I need to move forwards by 1/4 to land at S4. Now I need to move backwards by 1/5 to land at S5. And so on and so on. We get this spiral effect. This spiral effect is pretty powerful. Once we've done, it sure looks like every future term, S6, S7, S8, and so on forever, will be stuck here between S4 and S5. And this is true. So note. For any... This series has the property. Oh no, I didn't say Siri, I said series. I thought I turned this off. This series has the property that after Sn, all future partial sums sit between Sn and S minus 1, Sn minus 1. So between S4 and S3 fits S5 and S6 and S7 and so on forever. Is this obvious? Why is this true? Well, it's this alternating back and forth thing. We're always going to go the opposite direction of the last one because the negative 1 to the n always flips back and forth. We're never going to go past that last jump. The next one is going to be between the last two. The next one is going to be between the last two. What is it that makes, let's say, Sn, and then here's Sn plus 1. When I go to Sn plus 2, how do I know it's between Sn and Sn plus 1? It's because the An plus 2th term, the term that we added on after An, is smaller in absolute value than An plus 1 was. Meaning that this arrow takes us a shorter distance than that arrow. Which means this term is going to move back towards Sn but not pass it. The one after that is going to move towards the 2 terms ago and not past that. That's enough to get that the next one is, and that's enough to get that all the rest of them are in there. I assume there's a proof by induction you can do something like that. We're not going to write out the details, but I'm hoping this picture is convincing. The key things are the arrows only shrink, so you can't ever break out of the cyclone, and that the series is strictly alternating. It is positive, negative, positive, negative. There's never 2 positive terms in a row. So the next one is always switching direction and never going back further than we just came. I'm not going to go through an epsilon delta definition. We're not going that deep to prove that the series converges. But the key thing to know is that this sequence of even-numbered partial terms is decreasing and bounded below because it's never going to pass S1. The odd-numbered partial terms sequence is increasing, and it's never going to go past S2, so it's increasing and bounded above. How do I know that? To show that there's a limit, it's not enough that each of the odd sequences and the even sequences actually has a limit. We need to know that they are the same. The way I would know that they are the same, if I was writing out a detailed proof, was the idea that if these are decreasing to something, and if these are increasing to something that's different, then this gap, whatever it is, between that limit and this limit, is going to be bigger than the gap between Sn and Sn plus 1 for all n. But the gap between Sn and Sn plus 1 is 1 over n plus 1. Which is my stylus dead? Uh-oh, it hasn't died in a while. Oh, are we back? My stylus hasn't died in weeks. I hope this isn't a bad sign. The gap between those is an plus 1. Is 1 over n plus 1. And 1 over n plus 1 decreases to 0. So, fact, the alternating harmonic series does have a limit. It does converge. I believe it converges to natural log of a half. I think we'll see a way to see that later in the year. And this leads to what we're going to call the alternating series test. The alternating series test needs those three hypotheses that we used just now. If the sum, if an is a sequence of positive terms, I guess let's write down the series we're talking about. Let's start with, this is not good phrasing, but we'll do it because it's easier to understand. Consider the sum -1 to the n an. I've written this like it's an alternating series. I don't actually know it's alternating unless I know the ANs are always positive. The idea is this -1 to the n is supposed to make the thing positive, negative, positive, negative, positive, negative. That only actually works if the ANs are all positive. So the -1 to the n is the thing that's in charge of deciding. So if AN consists of positive terms, if AN is strictly decreasing, or is eventually strictly decreasing, does it need to be strict? If it's not strictly decreasing, then one of the arrows might equal the last arrow before it. Yeah, that's okay, as long as it eventually decreases eventually. Is eventually strictly decreasing. Doesn't have to be strict, I just said. Is eventually decreasing. And if the limit of AN is 0, then the sum of -1 to the n AN converges. This is the alternating series test. If you have an alternating series, this will give you that with pretty easy requirements. We need that the limit is 0, which is, like we've said, a bare minimum for even a chance at convergence. We need it to be decreasing. Well, if your limit is 0, you're probably decreasing, at least if you're positive. I guess we need it to be positive. If you have positive terms, stick a -1 to the n on them. As long as you're decreasing and you converge to 0, which are some pretty basic requirements, then that series converges. And the proof is just that spiral idea. The next one can't go further out than the last one. So once I tell you that this term is between the last two terms, all future terms will also be between the last two terms, because the next one is between these two, which was between these two, which was between these two, which was between these two. The arrows do shrink down to 0, so I can come up with if you give me an epsilon, I can find an epsilon gap so that all the epsilons are within the same window. That's what it means for a sequence to converge, is they eventually stay within epsilon of this limit. That's the alternating series test. But I haven't shown you the weird part. An alternating series, or a series of not all positive terms, can converge to the wrong thing. If you rearrange them. Note. Let's consider 1 plus a third plus a fifth plus a seventh plus a ninth plus ... This is the sum of the odd terms. These are... I guess they had negative on them when they were part of the alternating harmonic series. I want to split the alternating harmonic series into its odd terms and its even terms. The even ones are easier to understand. If I factor out the 1/2, I get 1 plus a half plus a third. I get the original harmonic series again, which we know the harmonic series diverges. The sum of those is infinity. And the odd terms are also divergent. For example, 1 is less than or equal to 1. 1/3. What do I have to do? Oh, 1 is bigger than a half. How do you do it? Oh. Oh, because, 1's bigger than a half. A third is bigger than a fourth. A fifth is bigger than a sixth. So 1 plus a third plus a fifth plus ... is going to be bigger than a half plus a fourth plus an eighth plus ... and we know that that's infinite. I can use direct comparison with the even terms. Because they are strictly decreasing, these odd terms are bigger than the following even term. And I know that the sum of the even terms is infinite because it's half of infinity. So this sums up to negative infinity. When I take the alternating harmonic series, -1 plus a half minus a third plus a fourth, the sum of the negative terms makes negative infinity. The sum of the positive terms makes positive infinity. I'm already in a place where when I split up the even and odd terms of a thing with all positive terms, I got the same thing. When I do that in this case, I get an infinity and a negative infinity, and it's not fair for me to say infinity plus negative infinity is, among other things, natural log of a half. Like, it kinda is, maybe. But it's even worse than that. If I can rearrange the terms so that it doesn't just do the infinity minus infinity thing, I can rearrange the terms so that it adds up to anything you want. Here's the place where I would ask the room, do you have a favorite number? But you're not in the room, so I'm going to use my favorite number. My favorite number is 210. Well, if I want to rearrange the terms of the harmonic series, I'm going to do it like this. I'm going to take positive terms. If I keep adding these forever, it goes to infinity. So at some point, I don't know when, it's going to pass 210. Stop the first time you pass 210. So I've added some of the positive terms of the alternating harmonic series. Now add the first term that's negative. Now that's probably set us below 110. Now add up some more even terms. 1 over 2m plus 1, 1 over 2m plus 2. At some point, we're going to get past 210 again. Now add the next odd term. That'll send us below 210. If it doesn't, keep adding negative terms till it does, but this 1/3 is so much bigger than these guys. We just barely passed 210. Adding on that negative 1/3 is taking us way back, setting us several terms behind. Now add even terms again. Until you get past 210. And I want to say you're just barely passing. Every time we add positive terms until we pass 210, stop the moment you're past it. So this 210, we added up a lot of terms to pass it, then we went back by 1. Then we added a lot of terms to pass it, and then we went back by 1/3. Going positive terms to pass it, back by another smaller amount. This series will use every term of the alternating harmonic series. This rearrangement uses every term of the alternating harmonic series, and it uses them all exactly once. Like, we're definitely going to hit all the evens. And I've used the first odd, then I used the second odd, I'm going to use the third odd. Every odd is going to get used eventually, and every even will be used eventually. And they're all getting used once. I haven't gone down as far as talking about the epsilons, but this picture is pretty convincing that the sequence of partial terms is going to get closer and closer to 210. No matter what window you want. Eventually, the negative terms will be smaller than that window, and it will never escape this window again. When we pass it and then go back 1, and then pass it and then go back 1, you can get it so that it always stays within epsilon, no matter how small your epsilon was. This rearrangement uses every term of the alternating harmonic series. It uses them all once. So when I say that the alternating harmonic series adds up to natural log of 1/2, it only adds up to that if you leave it in this order. The order that you add the things in matters. And this feels terrible. Like, that's not what adding is supposed to do, but it's a thing that happens now that we're trying to add infinitely many numbers. So we want to be able to say, well, that converges, but not really. I want to say that when I have a series of positive terms and it converges no matter what order you put them in, that's better convergence. That's really converging. That's a series that converges. I believe the word for this, for adding up to the same thing no matter what you rearrange it as, is called unconditional convergence. We don't really use that word in this class because when the things you're adding up are just numbers, unconditional convergence is the same as the word that we do use, which is going to be called absolute convergence. We say a series, sum an converges absolutely. I'll give it from 1 to infinity, but if it's not a 1, it doesn't matter. We say this series converges absolutely. This word is for a series, not for a sequence. When the series would converge if you added absolute values. When the sum with absolute values converges. It's an easy mistake to make in math to think that when someone says something happens absolutely, they're saying they're like putting emphasis that it definitely does, or that it's like an extreme thing. The word absolutely just means with absolute values. It doesn't mean the thing that you think it means in English. It's always really disappointing when I remember that. They're just talking about absolute values. When you make it positive, it converges. It is a fact that when you have a series of positive terms, so when this happens, the trick that we just did with the 210 can't happen. If you add up the positive terms, it's never going to go past 210. And if you add up the negative terms, it's never going to go backwards forever. The sum of the positive terms is finite. The sum of the negative terms is also finite. This means that when a series converges absolutely, it converges to the same thing no matter how you rearrange the terms. Even if it has some positives and some negatives, the sum of the positives is this number, the sum of the negatives is that negative number, so the thing you add up when you add all of them will always be that positive plus that negative, and that's it. You try and rearrange them in some goofy way, I can always say, well, what did the positives add up to and what did the negatives add up to, and that's going to be the limit of the whole thing. There's going to be some point where you have included enough of the positive terms that you've gone past, that you're this close to the positive sum, and you've included so many of the negative terms that when you add them all up, they'll be this close to the negative one. So anything that uses this many of these will be this close to the total sum, and yeah. I'm not going to try and write out a proof of this, but this is a fact. And when it converges to the same thing, no matter what you rearrange the terms as, that has a name. It's converging unconditionally. And in our context, where the only things we're adding up are numbers, converging absolutely and converging unconditionally are the same thing. But there is a separate word for that that needs to be distinguished in other higher dimensional contexts. Right. If a series converges but not absolutely, we say it converges conditionally. Converges conditionally because it doesn't always converge. It converges depending on what order you put them in. If we're obsessed with the question, does it converge? Does the series converge? The answer is it converges in this order, but it won't always converge in every order. I got it to converge to 210. If instead of taking positive numbers to go past 210 and then add a negative term, then past 210, if I'd gone past 1,000, then go past 1,000,000, then go past 1,000,000,000, I can come up with a rearrangement that goes to infinity. I can also come up with a rearrangement that goes to negative infinity. I can also come up with a rearrangement that gets close to positive infinity, then even closer to negative infinity, and then even closer to positive infinity. Like you can get it to go big, and then big negative, and then even bigger positive, and then even bigger negative. So it goes to both, kinda. Goes to is no longer the right word, but it will get close to there over and over. You can make it do anything you want. Conditionally convergent series are weird, and you kind of want to say they don't really count as convergent, but we already said what convergent means. It's just the limit of the partial terms exists, and if you converge, then then the limit of the partial terms does exist. So that's it. So at this point, the complicated language I gave us for the instructions, like I've been saying, our job is check if the series converges, but the instructions were always way more complicated in the homework than just does it converge. And now this sentence should make sense. Determine if the series converges or diverges. If it's an alternating series, and this is the only place where, like when you need positive and negatives for the question to get interesting. Also determine if it converges absolutely or conditionally. Those are the two different kinds of convergence. If you use a test, say what you're doing, clearly indicate why the necessary conditions to use it are satisfied. If the series happens to be a geometric, evaluate it as well. This is like a tricky extra thing thrown on. Most of these series are not geometric, but if I hand you a geometric series, you might as well be able to say, oh, by the way, this is one of the very few cases I can tell you what the thing adds up to. Let's talk about a series. So there's three possibilities for an alternating series. Let's give the alternating series a name. Sum -1 to the n an, where an is positive. Possibility 1 is that it converges absolutely. To show this, we show the sum an converges. This is not the same as the original series because now there's not a -1 to the n there. If an is positive, this is the same as sticking absolute values on the series. I guess I should write out, we show that the sum of absolute value -1 to the n an, which is the sum of an, converges. If it would have converged without the absolute values there, then it really, really converges. This is the best convergence where the order doesn't matter. Option 3 is that it doesn't converge at all. Probably will show that it doesn't converge. Use the divergence test. Remember, the alternating series test is really, really easy. To use the alternating series test, all we need to know is that this sequence of positive terms, which I've assumed that it's alternating, it needs to have a limit of 0, which is a bare minimum, and it needs to be decreasing. Well, if your limit is not 0, then you automatically didn't converge, and that's probably the way we'll show that. If you're not decreasing, that doesn't tell us anything. It just means we're not allowed to use the alternating series test. We'll see an example like that in a second. Have I put that in the homework? Yeah, I got all sorts of goofy stuff in the homework. So yeah, maybe it doesn't converge, and when it doesn't converge, probably we're stuck using the divergence test, because by and large, like, if the limit is 0, then probably it's decreasing and we can use the alternating series test and it converges. If the limit is not 0, we automatically know it doesn't converge it diverges by the divergence test. That just leaves the possibility that the limit is 0, but it doesn't decrease, and that does happen. I'm going to talk about one that does like that in a second. The middle option is the hardest. So this is where it doesn't converge. This is where it converges absolutely. Option 2 is when it converges conditionally. The definition of converging conditionally is that it converges, but it doesn't converge absolutely. That's what we have to show. I've used an it that I probably shouldn't have. The definition of this is that the sum of -1 to the n an converges, but not absolutely. How do I... Usually, you use the alternating series test to show it converges. To show what converges? To show that the sum of negative 1 to the n an converges. And then use techniques we've seen to show that the sum of an doesn't converge. And I should emphasize that this is the absolute value of negative 1 to the n an is the sum of the absolute value of an. Diverges. The middle one has two options, or has two requirements to show. The middle one is the hardest and the longest to write out. Usually the outer options are pretty fast to get written down, and the middle one takes like half a page. When you have when you have an alternating series, figuring out which of these situations you're in is the most important thing. If it converges, so the fact that this isn't true is this line. The fact that this isn't true is most of this line. The alternating series test mostly just wants the limit to be 0. You also need the terms to be decreasing, but that's such a small requirement. If your limit is 0 and you're positive, probably you're decreasing. I can come up with sequences that go down and up a little bit and down and up a little bit that do go to 0. Right. Let's do some examples of alternating series. Let's consider the sum of negative 1 to the n over n to the 3/2. From n equals 5 to infinity. Oh no, this series starts at 5. That doesn't matter at all. Like, not using the first few terms, nobody cares. This is alternating. It's really easy to get into a trap of thinking about the series 1 over n to the 3/2 is positive. Does it go to 0? It does go to 0. Is it decreasing? It is decreasing. So we can use the alternating series test. The alternating series test will tell us it converges. And that'll answer it. No, that doesn't answer it. That'll tell us that it converges, but it won't tell us if it converges absolutely or conditionally. If it converges absolutely, the alternating series test was worthless. If it converges conditionally, then we probably did need to use the alternating series test, but I shouldn't start writing that out until I've worked out if it converges absolutely or not. So, it does converge, but maybe it converges absolutely instead of conditionally, in which case writing out the alternating series test is not helpful. Does it converge absolutely? What does it mean to converge absolutely? That means, well, does it converge absolutely? Does it converge with absolute values? What is the absolute value of negative 1 to the n over n to the 3/2? That's the sum of 1 over n to the 3/2. Does that converge? That's a p-series. The p-value is 3/2. That's bigger than 1. So yes, it does converge. That means the alternating series test was no help. What we needed is just to show that it converges absolutely. We show that it converges absolutely by throwing absolute values on it and showing the new thing converges, and in this case there's nothing to show. We recognize that series as a p-series. So, let's answer it. The given series converges absolutely. Since the sum of absolute value negative 1 to the n over n to the 3/2 is the sum of 1 over n to the 3 halves is a convergent p-series. It's going to be tempting to say here p equals 3 halves is greater than 1. I don't know if I need to put that last bit, which is why I put it in parentheses. I'm adding that in to make it totally clear why I know it's convergent. 3 halves is bigger than 1 is the thing that I'm seeing. This is an example of the easy one. A thing that's likely to happen is you get something that's harder to show that it converges. Maybe you're going to need to use direct comparison on this. Maybe you're going to have to use limit comparison on that resulting series. Here was the easiest possible version where when I threw the absolute values on, by which I mean when I got rid of the negative 1 to the n, I was looking at a series that I immediately knew right away. There will be times that there's more work necessary, and it'll be just as bad as any of the other problems have been. And we'll see some like that. Oh man. Sorry, I can't stop yawning. I already got my coffee here too. I can't go get more coffee to fix it. The series converges absolutely because when I throw absolute values on it, I'm looking at a convergent p-series, so it converges with absolute values, is the definition of converging absolutely. Let's do a different one. Let me get my notes out. Do I have... Consider the sum from n equals 2 to infinity. Negative 1 to the n times n to the 4th over n squared n cubed minus 1. What's going on with this guy? Again, I think about the absolute series. What happens if I get rid of the negative 1 to the n's? If the result, if this thing converges, then the original converges absolutely and I'm done. If this thing doesn't converge, then I'm worried about maybe it converges conditionally or maybe it diverges and I have to figure out which is which. Does this series converge? Usually I'm thinking about how much bigger is the top than the bottom, like about how big is this? N to the 4th over n cubed minus 1 is about as big as n to the 4th over n cubed, right? The minus 1 is not affecting it much. If I'm doing back of the envelope estimates on how big are these terms, the top term is n to the 4th. The bottom term is about as big as n cubed. How big is n to the 4th over n cubed? It's n. Does the sum of n converge? The sum of n does not converge at all. Like that didn't even have a chance at convergence. So this one probably also doesn't. How would I show that this didn't converge? Probably the divergence test. The terms are getting bigger and bigger. To converge, the terms should be getting smaller and smaller, closer to 0. Here, these are not. So, the divergence test should probably also work on this one, when there's a negative 1 to the n there. Let's try that out. We want to show... Oh, I shouldn't be erasing this. This is bad teaching. We want to show that the series diverges by the divergence test, we think. I'm going to start writing it, assuming that that's going to be true. Here's the thing that I'd like to say that is difficult. I want to say the limit of n to the 4th over n cubed minus 1 is not the sum, the limit. The divergence test talks about the limit of the terms, not the limit of the partial sums, not the sum of the terms. This limit is infinity. I took a pre-calc class, I'm allowed to say I know that. The degree of the top is bigger than the degree of the bottom. It's rational function, big numerator, little numerator. Like, we know this from pre-cal. I want to say that the limit of negative 1 to the n to the 4th over n cubed minus 1 is also infinity. Or wait, no, it's plus or minus infinity, because the thing is alternating between positive and negative. That's not a thing that makes sense as a term. You don't say the limit is positive or negative infinity. Like, if I did say that, probably what I mean is the limit is infinity or the limit is negative infinity. This limit is neither. I get get big positive numbers and I get big negative numbers, and I'm alternating between the two. So I'm not allowed to just say the limit is infinity. If I could phrase it that way, it's really easy to say the limit is not zero because it's infinite. But the wording I have to use is a little more awkward than that. I don't want to say something that's not true. I'll say we have the limit as n goes to infinity of n to the fourth n cubed minus 1 is plus infinity. And so the limit with the negative 1 to the n there, I'm not going to claim that it is anything. I'm just going to say it doesn't exist. And in particular, isn't zero. Done. The limit's not zero, so you fail the divergence test. You cannot converge at all. Okay, so far we've done the two easy versions, where it diverges by the divergence test, or it converges by the... it converges absolutely, in which case this other series converges. I want to take a second and emphasize, if I ended this with saying so it converges, I know I hit this hard yesterday, I'm going to hit a little bit hard too. This word it, what are you talking about? Instead of it, maybe I can say this series. I'm already in a situation where I was talking about two different series though. Like this series got talked about and this series got talked about. And each of those represents a sequence of partial sums. So there's already two series and two sequences implicitly being talked about. Be so careful with your its. Be so careful with your antecedents. Make sure that every noun phrase you use, it is easy to tell what noun phrase you are talking about. The things that can converge in these conversations are so many. Okay. Oh, no, I said talk to... this series is different from this series. This is the same as this one, because that's what the equals is telling us. Okay, but there were two different series being talked about, is the point I was trying to make. I kind of messed that up. Let's do one of the in-between cases. How about... the sum from n equals 1 to infinity, negative 1 to the n squared over n times 1 plus root n. Nope, that one doesn't work. That reduces too much. Negative 1 to the n minus 6 over n 1 plus root n. Yes, that works. Okay, what's going on here? What is my negative 1 to the n in front of? This is about as big as negative 1 to the n times that thing on top, n minus 6, is about the size of n. The ratio between 194 is not significant. On bottom, what do I have? I have about n times root n. My thing is about as big as negative 1 to the n times 1 over root n. Does the sum of 1 over root n converge? Does the limit of 1 over root n equal 0? These are the two big questions I want to answer right away. If the answer here is yes, then the original converges absolutely. And this is the way. And I don't need to think about the limit. The limit must be 0 because it converges. If the answer is no, that the limit is not 0, then the original diverges by the divergence test. And this is the way. If I get a no answer to this question, then this is the correct thing to think about. If I get a yes answer to this question, then this is the correct thing to think about. If neither of those is the case, then I have to have thought about both of them, and I need both of them to get to the middle case, which is called absolute convergence. Let's try this out. Which is, no, it's not absolute convergence, it's conditional convergence. Conditional convergence is the in-between case, where I will use the alternating series test to check that it converges. So let's get back to the words real quick. What's conditional convergence? That's when a series converges, but not absolutely. This thing is going to be the thing that shows me it doesn't converge absolutely. I'm going to have to write out my explanation that this doesn't converge. This thing is going to be used for the alternating series test, which is going to be what tells me that it converges. We'll get that it converges by the alternating series test. We'll get that it doesn't converge absolutely by this piece of reasoning. So, what do I got to do? I think I've convinced myself. Does the limit equal 0? The limit does equal 0, yes. Does that series converge? That series does not converge, no. It's a p-series with p equals 1/2, doesn't converge. So we're going to be in the conditional convergence case. We got to be able to write out all this stuff. Let's start by showing that this thing doesn't converge. And it's not this thing I want to show doesn't converge, it's that thing with the absolute values. The series doesn't converge absolutely. With this sentence, I'm making a claim that I haven't justified yet. And I think it's good form to put a colon after this to say, you're not supposed to believe me yet, I'm about to show you why, but I'm putting this sentence up front so you understand the context of the sentences I'm about to consider, right? The series doesn't converge absolutely. Colon. Since consider the sum with absolute values on it. Oh geez. What happens when I throw absolute values on it? I want to say all the absolute values do is get rid of the -1 to the n. Ooh, but it doesn't, because n minus 6 is sometimes negative. Dang. So I need to add a sentence accommodating that. Since the absolute value of -1 to the n minus 6 over n 1 plus root n equals n minus 6 over n 1 plus root n. I want to say this is true eventually. To convince someone that it's true eventually, it's more convincing if I tell them exactly when it is true. This is true for n greater than or equal to 6. That's when the top stops being negative. And so now the thing on the right is always positive, and it does equal the absolute value of the thing on the left. It's enough to show that the sum of n minus 6 over n 1 plus root n diverges. This has a few negative terms at the front, but it's the part at the end that determines whether it diverges or converges. Those few negative terms don't mean anything. This isn't quite the absolute convergence, but it equals the same past the 6th term. That's why I'm saying it's enough. This is close enough to the original. Why do I know that this thing diverges? This diverges. I want to use limit comparison with 1 over root n. Actually, can I use direct comparison? To use direct comparison, I want to show that you are bigger than something that's infinite. The sum 1 over root n would be infinite because it's a p-series, Is 1 over root n smaller than that? 1 over root n equals n over n root n is small. No, you're not making the top bigger, you're making the top smaller. So it's going in the wrong direction. Direct comparison doesn't work. So limit comparison is usually the thing we go to. Let's try that out. We do this by limit comparison. The limit as n goes to infinity of n minus, so I'm now in display mode. I think I used the word display mode a bunch last time without explaining what I meant. Do I have... Let me load up a math paper and show you what I mean. I mean, sometimes in math you stop and you stop being in paragraph form and you just put a bunch of math in the middle of the page. This is where I am. This limit is the limit as n goes to infinity of, I want to multiply by root n on top. N to the 3 halves minus 6n to the 1 half over n to the 1 plus n to the 3 halves. I'm going to multiply the top and bottom by 1 over n to the 3 halves. I get the limit of 1 minus 6 over n over 1 over root n plus 1 equals 1 minus 0 over 0 plus 1 equals L equals 1. Since the sum of 1 over root n diverges, why? It's a divergent p-series. We have that. Here's a place where I'm tempted to say the given series diverges, but the given series had negative 1 to the n on it. We're talking about something different. We have that the sum of n minus 6 over n 1 plus root n diverges. And the given series, and so the given series doesn't converge absolutely. Cannot converge absolutely. I'm tempted to explain that that's not quite the same as itself with absolute values, but I already explained that here. Okay, this is like halfway through. We've shown that the series doesn't converge absolutely. I'm putting a box around it because we're still going. But the given series does converge. The sequence, how do I know it converges? It converges by the alternating series test. I guess I might as well say in this first sentence that I'm using the alternating series test. You're welcome to use AST as an abbreviation for alternating series test. Like, using acronyms like this isn't good in math writing, but if you're on an exam, time is short. It's okay to use your shorthand. Like, the goal is good sentences. You don't need to prove to me your penmanship or anything. The series does converge by the alternating series test. What do I need to show for the alternating series test? I need to show that n minus 6 over n 1 plus root n is eventually positive. When is it positive? Once n is greater than 6. Has a limit of 0. Since limit as n goes to infinity. N to the 1 minus 6 over n plus n to the 3 halves. Again, I multiply the top and bottom by a 1 over n to the 3 halves. And I get 1 over root n minus 6 over n to the 3 halves over 1 over root n plus 1 is 0 minus 0 over 0 plus 1 equals 0. I should have a limit here. This is the same, multiply the top and bottom by 1 over the biggest thing on bottom. The size of the bottom is about n to the 3 halves, so I multiply the top and bottom by 1 over n to the 3 halves. Since the top is smaller than 1 over n to the 3 halves, the top becomes stuff that is all zeros, but I have a 1 on bottom. It's important that I end up with the 1 on bottom so that I have 0 over constant instead of 0 over 0. 0 divided by 0, you can't tell what the limit is, but once I've got it in the form of 0 over something that's not 0, that limit does exist and it is 0. We said that it's positive, it has a limit of 0, and is eventually decreasing. How do I know it's eventually decreasing? Oh, that is not obvious at all. I guess I want to say that its derivative is going to be negative. The derivative with respect to x of x minus 6 over x plus x to the 3 halves. I sure hope it's easy to see that this thing is negative once I take the derivative. It's going to be pretty gross. I should probably do this off on scratch paper before I try and fold it into my paragraph. What's the derivative of this? It's derivative of the top. Leave the bottom alone. Minus leave the top alone. Derivative of the bottom. 1 plus 3 halves x to the 1 half. All over bottom squared. The bottom is definitely positive. For a fraction to be negative, I want to know that the top is negative, or eventually negative. So I guess I want to FOIL out the top. I got x plus x to the 3 halves minus, when I FOIL this out, I'm going to get first is x, outside is 3 halves x to the 3 halves, inside is minus 6, last is minus 3 halves x to the 3 halves. Oh, I did last wrong. That was supposed to be minus 9x to the 1 half. So I got this minus this. So the x minus x cancels. This is going to be negative 1 half x to the 3 halves plus 6 plus 9. It's not 9x to the 3 halves, it's 9x to the 1 half there. I can't FOIL the last term out for some reason. Plus 9x to the 1 half over something squared. How do I show that this is negative? Like, the key thing is that this is the biggest term on top, and it's the negative one. Do I multiply top and bottom by negative x to the 3 halves? Yeah, that'll work. The derivative of this, I'm not going to write out the quotient rule. I'm writing to a grown-up audience. They don't want to see me simplify gunk like this. The derivative of this turns out to be negative 1 half x to the 3 halves plus 6 plus 9 x to the 1 half over what was inside here? X plus x to the 3 halves squared. Let's multiply the top and bottom by 1 over x to the 3 halves. Now the top is negative 1 half plus 6 over x to the 3 halves plus 9 over x over x plus x to the 3 halves squared x to the negative 1 half. The numerator means top, approaches negative 1 half, so is eventually negative. While the bottom, the denominator, is always positive. On x greater than 0. Okay, so we don't need this stuff anymore. If you're turning in an exam, like, turn in your scratch paper. But I'm cutting it. And, hey, look, now I've reached a place where this parenthetical has gotten too big to be a parenthetical. I should split this off into a separate sentence. Okay, let's start rewriting here. The series does converge by the alternating series test. This thing is eventually positive, once n is greater than 6, and has a limit of 0. Since this. That doesn't need to be in a parenthesis either. And has a limit of 0, comma, since this reason. Also, since the derivative is this, it's negative 1 half x to the 3 halves. This one's a huge pain to talk about the derivative of. I won't make something so gross on the test. Actually, this isn't a good way to do it. This stuff is way too gross to stick inside a paragraph. Let's do a little display. Now consider f of x equals x minus 6 over x plus x to the 3 halves. Math display. F prime of x is I'm doing something which is kind of bad form. I'm talking about this function at random without explaining yet why I'm talking about it. Part of the flow of this paragraph is I'm going to get through this real quick and then come back and say why we were talking about that when I wrap it up. Okay, the derivative is this. The numerator approaches negative 1 half, so is eventually negative. While the denominator is positive on x greater than 0. This means eraser, that's what I'm looking for. Consider this function. Its derivative is this. The numerator approaches negative 1 half, so is eventually negative, while the denominator is positive. So, this means, what have I used? I feel like I've said so too many times. This means, I shouldn't use so because it's not obvious why I'm talking about this still. This means f prime of x is eventually negative, so is eventually decreasing. And so the sequence n minus 6 over n plus n to the 3 halves is eventually decreasing as well. I guess I should write this in a line. I get so bad at staying inside the lines. n minus 6 over n 1 plus root n is eventually decreasing as well. So the alternating series test does apply. I'm restating my first sentence. Like I said, it converges by the alternating series test. We've checked that the thing is positive, has a limit of 0, and is eventually decreasing. So the alternating series test does apply. Should I restate my conclusion that the series converges? No, I think we've connected the dots to the first sentence enough that this makes sense. I need to get to where I'm going. We showed the series doesn't converge absolutely. We've shown that the series does converge. That means, by definition, it converges conditionally. I should make a sentence that says that. Thus, or we've shown the given series doesn't converge. Doesn't converge absolutely, but does converge. Hence, it converges conditionally. I'm trying to tie together the last two paragraphs that so far had nothing to do with each other. The first paragraph showed that it didn't converge absolutely. The second paragraph showed that it did converge. The first by, I think we used limit comparison. I don't need to restate that it was by limit comparison, although I probably could, just to remind someone how we got here. Right, what else should I have done? I think better writing would have involved putting an indentation here. This should be its own separate paragraph. Paragraph 1 was showing that it doesn't converge absolutely. Paragraph 2 is showing that it does converge. Note that this thing is not a new paragraph. A line of math doesn't need to be, like, do I have a... I feel like I need to pull out some actual math and show you what is the style of mathematical writing that I'm aping here. Close. Stop pulling out my own paper. Do I have some other people's papers to pull out? Grad school? I had an ergodic theory term paper. Here's something from Aiken. I think I'm only a co-author on this one. Show me what this looks like. Give me a math display in here. Yeah, here's one. Here I got this goofy math display, but the next line after it, which is again another complete sentence, is not indented, meaning that this whole thing is one paragraph. You can put a math display in the middle of a paragraph and it doesn't cause you to reset your paragraph, even though this thing doesn't look like an indentation. This type of setup is like, this is how you typeset math, and this is the flow of reasoning that we're trying to indicate here. This indentation is indicating a new paragraph. This indentation is not. The lower indentation is because I've got a big math display thing going on. We've shown the given series doesn't converge absolutely, but does converge, hence it converges conditionally. Boy, this is gross. We've done one of each. I owe you guys a lot more examples of everything. But this is the weird, difficult situation where when you have series that aren't all positive, you need to be thinking about this much higher level, more difficult possibility of converging conditionally. When it doesn't converge, it's almost always just by the divergence test. When it does converge absolutely, you're basically just ignoring the -1 to the n and showing that thing converges, which you do the same old ways. It's this middle one that's the worst. We got 2 more tests to state. These kind of come from considering things that are almost geometric. We're going to talk about power series pretty soon, and these 2 tests are the best tests to talk about for that. They're called the ratio test and the root test. They both come from the idea that if an is basically like a constant times r to the n, and we know, so maybe you've got something that's kind of geometric. If you're like this with r bigger than 1, then the series should diverge. And if you're about as big as a times r to the n with r less than 1, but positive, then the sum of an should converge. So the question we want to ask is, if my series is, if my terms are kind of geometric, they don't have to be exactly geometric, but if they're approximately geometric, how do I figure out what their growth rate would be if it was geometric? If you're acting geometrical, how can I figure out if you're actually geometrical? How do I figure out what is it that you're scaling by? How do I look at the sequence that's a times r to the n and figure out what the r value is? And there's 2 ways at that. If I have, let's take a series that starts with 10 and doubles every step. Actually, let's double and add 1 every step. 10, 21. Double that is 42, plus 1 is 43. Double that is 87. Double that is 160, 174, but I'm going to add 175. Double that is 350, plus 1 is 351. This should be about doubling every step, right? Maybe you end up with a factor a little bit bigger than 2 or something like that. But if you are about doubling, how do I check that you're about doubling? Well, there's 2 ways. I can talk about the ratio of terms. 21 over 10. 43 over 21. 87 over 43. 175 over 87. Does this approach 2? This idea is going to be called the ratio test. You check if something is basically geometric by asking for the ratio of consecutive terms, and if that ratio limit exists, if the limit is bigger than 1, then you are basically geometric with a growth factor bigger than 1, so you must diverge. And if the limit is less than 1, then you are basically geometric with a growth rate less than 1, or with a decay rate between 0 and 1, so you should converge. There's another way to get there too. If this sequence is about something times r to the 1, this is about something times r to the 2, this is about something times r to the 3, I can try and pull off the r by taking the nth root, the first root here, the square root here, the cube root here, the 4th root of a r to the 4. When I take the 4th root of a times r to the 4, that's going to be the 4th root of a times r, with maybe there's an absolute value going on. When we write the formal version, there will be absolute values. But I get about the 4th root of a times r. I'm going to get a to the 1 over n times r. Like, ugh. If my term is about as big as a times r to the n, then the nth root of it will be about as big as the nth root of a times r, right? And now how big is the nth root of a? That's a to the 1 over n. When n goes to infinity, 1 over n goes to 0. This will go to a to the 0, which is 1. The limit of the nth root of n is likely to be just the r. The ratio of terms is the thing I'm likely to think about most when I'm talking about something that's kind of geometrical. But the nth root kind of does just the same thing. These are going to be the ratio test and the root test. And spiritually, they are brothers or sisters or whatever. I don't need to gender the theorems. in that they are both measuring, are you kind of like a geometric series? Well, then, which geometric series are you like? Let's state these. The ratio test. If the sum of absolute value an plus 1 over absolute value... Wait. Let's try this. Suppose... How did I write it on my thing? Stop trying to freehand it. Read your notes, Andy. Ratio test. If an is positive... It doesn't need to be positive. This is bad notes. Don't look at your notes so much. Okay. Let's try this. Let rho is a Greek r. We're using it to represent the r-like thing. Let rho be the limit as n goes to infinity of the absolute value of an plus 1 over the absolute value of an. It's the next term divided by the current term. If it exists. If rho is bigger than 1, then the sum of an diverges. You are like a geometric series with a common ratio that is bigger than 1, so you diverge. If rho is less than 1, then the sum of an converges. If the limit equals infinity, that counts as bigger than 1. Yeah, that's it. Not only does it converges absolutely. If the series was already all positive terms, the absolutely is not adding anything, is why I put it in parentheses. If the series had some positive, some negative, well, the thing I'm talking about is the absolute values. This test, I'm already thinking about a version of the series with absolute values. If the test works, then it worked with absolute values, because the absolute values were already there. You get absolutely for free. The root test is a very similar deal. Let rho be the limit as n goes to infinity of the nth root of, I want to say the nth root of a sub n, but I'm going to put absolute values there again, because I don't care if the things were positive or negative. Multiplying by a factor of -2 is going to make you diverge just as much as doubling does. Multiplying by a factor of -1/2 will let you act. And if you use sometimes positive a half, sometimes negative a half, that doesn't matter. Consider the nth root of the absolute value of an, if it exists. Or is plus infinity. I would ask about negative infinity, but this thing is positive. You can't go to negative infinity with positive numbers. If rho is bigger than 1, then the series sum of an diverges. And if rho is less than 1, then the sum of an converges absolutely. Again, you get absolutely for free because we threw an absolute value on in the original problem. We were only ever thinking about the absolute value one. Cool. These are the ratio test and the root test. When you are using these, the ratio test is great for if you have an n factorial. I'm not excitedly saying that it's great for n. I'm saying it's great for n factorial. N factorial is kind of a blind spot for most of the tests. If you think about how big is n factorial, it's hard to say that n factorial is bigger than something or less than something. We just don't have many good inequalities for n factorial right now. You don't have the ability to integrate it with the integral test. There's no function x factorial you can try to integrate out to infinity. By and large, if the problem you're doing has an n factorial in it, there's a good chance the ratio test is the best way to deal with it because it makes the factorial go away. And we'll see an example of that in a second. When you have the root test, not the Groot test. I'm starting to write Groot test. I'm so excited about the Groot test all of a sudden. The root test is good for... Oh, I was saying good for. That's what I was saying. It's good for if you have stuff to the n. The root test is a lot of times the least useful one, but you only really pull it out if you have some mess that's all being raised to the n or something. Let's try some problems where we want to do these. Consider the sum from n equals 0 to infinity 1 over n factorial. We'll use the ratio test. The limit as n goes to infinity, or maybe I should give these things a name. Let an be 1 over n factorial. Then the limit as n goes to infinity of the absolute value of an plus 1 over an. I'm making it clear that this is what I'm starting with because this is what the ratio test wants. If I just start with the next line, it won't be obvious that this is connected to the ratio test, is why I'm adding this in. This limit is the limit as n goes to infinity of absolute value 1 over n plus 1 factorial divided by 1 over n factorial is the limit as n goes to infinity of n factorial over n plus 1 factorial. What does n factorial mean? If you haven't seen it, I think you should have seen it in Cal 1. N factorial is 1 times 2 times 3 times 4 times ... times n. 0 factorial is 1 if you didn't know. N plus 1 factorial is 1 times 2 times 3 times 4 times, go all the way up to n plus 1, which means the one before that was n. These fractions cancel. This is the cool trick that makes the ratio test worthwhile for when there's a factorial, is this lets us redo a thing so that it no longer has any factorials in it. This turns into the limit as n goes to infinity of just 1 over n plus 1. That limit is 0. 0 is less than 1. Crap, I can't start a sentence with the statement 0 is less than 1. I guess I could write it out. I'll say since. I'll put a since so that I don't have to start with 0. Since 0 is less than 1, the given series converges by the ratio test. Cool. Cool. How about... Oh, a thing I should have said out loud. What do you get if the limit is 1? If the limit is 1, you don't learn anything. If the limit is 1, which it is very often, like, you think about the harmonic series. The harmonic series diverges. That's one of our baby examples. We definitely know the harmonic series diverges. This should be very easy. The ratio test should be very easy to work out here. Well, if I think about the limit of an plus 1 over an, I get 1 over n plus 1 over 1 over n. That's n over n plus 1. That limit is 1. The ratio test tells us nothing about the harmonic series. You think about it, a geometric series, if it converges very fast. If it diverges very fast. When a series is acting geometric, it's acting very geometric, right? Those are not close to the border of maybe it converges, maybe it doesn't. They either definitely converge or they definitely don't converge. If something's behaving exponentially, it's either getting big very fast or getting small very fast. The things that are on the borderline, which we kind of think of the harmonic series as being close to the edge between convergence and divergence, it's not behaving exponentially, one way or the other. So the ratio test and the root test, they are useful in the times that they are useful, but in a real specific way, they're not that helpful at all. They don't, when you have something that's tricky, the ratio test and root test are not likely to be the answer. But when you have something with factorials, it's really nice to have the ratio test to turn it into something really simple. Let's try, let's do one with for the root test. Let's do the sum of basically you're only ever going to use it when you have a whole bunch of stuff all to the n. What could I raise to the n? I don't know, 2n minus 1 over 3n plus 2. If an equals 2n minus 1 over 3n plus 2 all to the n, then the absolute value of the nth root of the absolute value of an is the nth root of the absolute value of this is going to be the absolute value of 2n minus 1 over 3n plus 2, which is going to go to 2/3. Since 2/3 is less than 1, the series converges by the root test. Usually when it's time to use the root test, it's pretty obvious because the stuff is all being raised to the n. There are not many situations where you would use the root test that are not for that. Okay, we've seen all the tests. I believe I still have... I got some hiccups. I always get... it's because I drink too much coffee. I have not done enough examples of looking at a series and saying, how do you do the test? I've been prioritizing getting through all the tests fast so that we can get them all on the board and think about them in big terms. Now I know you use several days of just doing examples of figuring out which test to use, and if it's alternating, doing some of that stuff. The alternate, let me fill in these gaps. Let rho be the limit of an plus 1 over an. If rho is bigger than 1, the sum of an diverges. If rho is less than 1, the sum of an converges. Here let rho be the limit of the nth root of absolute value an. Same deal. If rho is bigger than 1, the sum of an diverges. If rho is less than 1, the sum of an converges. I should add in absolutely. The alternating series test. If an is positive, decreasing, and an goes to 0, notice that these are independent. A sequence can decrease but not closer and closer to 0. A sequence can be positive and approaching 0 but still not be strictly decreasing. If you get smaller, you're allowed to get bigger once in a while and still get closer and closer to 0. Then the sum of an converges. The sum of negative 1 to the an converges. But we don't know if it converges absolutely or not. And that's the big warning. Very rarely are you going to have a problem where you just do the alternating series test and it's easy and you're done. Because if you're using the alternating series test, you're probably trying to show that something converges but not absolutely. In which case you need to show that it doesn't converge absolutely. You at least have that much extra work to do. I want to show you one more example before we wrap it up today. So you now have all the tools to do the homework. Try doing the homework. I'm going to send some instructions by text, but what I'd like you to do is try and do 6 problems and send them to me. Over the rest of this week, what I want to try to do is examine some student work during class. It's awkward. It's really awkward. Like, we want to be having... The thing I need to be teaching you right now involves really fine, detailed conversations about don't use this word, or reorganize this sentence, or restructure this. And it feels really uncomfortable having someone talk about your work in that much detail, but it's the thing that we gotta do. So I'm going to text you and ask you, please write up a few problems and send them to me so I can throw them up on the board and we can talk about the sentences and are they in a good order and where's a place where this is phrased weirdly or where's a place where whatever. We're going to go through a few cycles of this. Probably we won't do the first one tomorrow. Tomorrow's just going to be me doing examples. On Wednesday, I want to... So Tuesday night, I'm going to tell you, do some homework, send it to me. Wednesday, we'll spend the day talking about problems you wrote up. Maybe again Thursday. I want to be headed towards having our exam a week from today. Right. Let me show you a problem first. Here's one that our tools are incomplete. And here's an example of why. Consider the sum from n equals 1 to infinity of sine n over n. This isn't sine n pi. Sine n pi was the thing that turned out to always be 0. Sine n, what does sine n look like? What does sine x look like? Sine x is alternating between positive and 1, giving us numbers big and small. Here's 1, 2, 3 is almost pi, 4, 5, 6 is almost 2 pi, and it starts spreading out. So sine 1 is going to be positive, 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 negative, 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 positive, positive, probably negative, probably negative. My sketch is getting pretty bad at this point. I'm getting these weird irrational numbers that are sometimes positive, sometimes negative. This has infinitely many positive terms and infinitely many negative terms. But it's not alternating. Part of the deal for an alternating series, the reason we have these statements with a -1 to the end there, is those need it to be strictly alternating. For the alternating series test to work, you need positive, then negative but not as much, then positive but not as much, then negative but not as much. This isn't doing that. I have 3 positives in a row that are small, big, or medium, big, small. Then I have 3 negative terms. Then I have 3 positive terms. The terms are generally getting smaller. I have a factor of 1 over n on there. Sine n, not sine n pi, just sine n. So sine n is never bigger than 1. Multiplying that by 1 over n, I get a number that's smaller than 1, then a number that's smaller than a half, and then a number that's smaller than a third. Sometimes it'll be much smaller, but at the very least it's not much bigger. This thing kind of acts like an alternating series test, but the tricks that we use, the alternating series test, doesn't work. We're going to have a couple positive terms, and then a couple negative terms, and then a couple positive terms, and then a couple negative terms. And they will generally be getting smaller and smaller over time. But maybe I get a pass where the negatives are both little and then the positive one is really big. So maybe the next one is going to be bigger than the last few. That's going to happen. But it turns out this thing does converge. The alternating series test cannot show us that this converge. The series doesn't converge absolutely, so that's not going to show that this converges. None of the tools that we have are good enough to show that this series converges. You have to go down to the limit of the partial sums, and even then it's just really bad. There's nothing you can do to, like, there's no simplification you can do for sine 1 over 1, plus sine 2 over 2, plus sine 3 over 3. What can you do to simplify it? Nothing. It's just a nightmare. So this is just to clarify that the things that you know how to work don't work on every series. Like, these tools are incomplete. Sine n over n does converge. If we have time, I have a little project I want to set you guys on that will involve evaluating sine n over n. Is it like pi over 6? I can't do it in my head. This turns out to be a number that you can evaluate. Yeah, what time is it? I guess I should do an example that we can do before we go. Actually, you know what? We're close enough to 6. I'm going to call it for today. To start taking a look at the homework. There are definitely some of these problems in here you can do. Some you need more examples of, but start thinking about them. 89 through 92 are all positive terms. Many of these things are positive. Start writing them up. 95 we just did. How would you do 96? How would you do 97? These are things worth thinking about. Yep, that's it. I'll see you guys tomorrow with some more specific instructions on writing some stuff up and turn it into me so we can start going over some student work. Take it sleazy, everyone. Goodbye.